All right, today we're going to do something a little different. Think of it like an architectural tour of algebra. Yeah, really. We're going to get our hands dirty and figure out what the fundamental building blocks are, these special structures that make the whole thing work. They're called polynomials. So you ever just look at an equation and wonder what's really holding it all together? We see these expressions everywhere, but what are they actually made of? What are the raw materials, the actual bricks and mortar that build the entire structure of algebra? Well, that's exactly what we're here to find out. Okay, so first things first. If we're going to build anything, we need to start with the raw materials, right? On our little algebraic construction site here, that means getting to know the two most basic components, constants and variables. I like to think of them as two types of friends. You've got your constant friend, the super reliable one who's always the same, no matter what. The number 5 is always just 5. Then you have your variable friend, usually represented by a letter like x. This friend is a bit more flexible. Their value can change depending on the situation, and you absolutely need both of them to build anything meaningful. So what happens when we take these raw materials, our constants and our variables, and we kind of fuse them together using multiplication? Well, that's when we create our very first building block. We call it a term. This is like our single solid brick. It could be super simple, like just the number 3, or just a variable, like x, or a combo, like 2x. Okay, so now we have our bricks, our terms. The next logical step is to start connecting them, right? We use addition and subtraction as our mortar, and when we stick these term bricks together, we build a much larger structure, an algebraic expression. All right, now that we know how to build a basic algebraic expression, we can get to the main event. Because here's the thing. It turns out not all of these expressions get to join the very exclusive polynomial club. Nope. There's a very specific and honestly a surprisingly simple rule for getting in.
So let's look at this one. Here we have a structure built from our terms. We've got x cubed, 5x squared, minus 2x plus 9. They're all cemented together. It's a totally fine algebraic expression. Looks solid, seems well built.
But here's the real question, the one that gets right to the heart of it all. What's the secret ingredient here? What's the one special property that takes this thing from being just a regular algebraic expression and elevates it into the special category of a polynomial? And here it is, the big reveal. This is the one simple rule that separates them. For an expression to be a polynomial, the power, the exponent on every single variable has to be a whole number. I mean it, no fractions, no negatives, just 0, 1, 2, 3, and so on. That's it. That's the entire secret. And this just lays it out perfectly, right? On the left, you've got the ones that are in the club. Their exponents are all nice whole numbers. But over on the right, these are the rule breakers. The square root of x? Nope, that's really x to the power of 1/2. That's a fraction. What about 1 over x? Also not allowed. That's x to the power of -1. See? They both violate that one simple rule, so they don't get to be polynomial. And this quote just nails it. It really sums up what we've just figured out. All polynomials are algebraic expressions, but not all algebraic expressions are polynomials. It's like a special, really well-behaved group within the larger world of expressions, and it's all thanks to that one little rule about whole numbers. Okay, so we can spot a polynomial in the wilds now. That's step 1. Now it's time to learn how to actually describe it. Just like an architect has specific names for a building's features, mathematicians have a whole system for classifying these algebraic structures. So the most important characteristic is something called its degree, and it's super simple. It's just the highest exponent you can find on any variable in the whole polynomial. A good way to think about it is like you're measuring the height of our algebraic building. And usually a higher degree means you're going to get a more complex, interesting shape if you try to graph it. So there are really two main ways we name these things. First, we can classify them by the number of bricks, the number of terms. If it has 1 term, it's a monomial. 2 terms, it's a binomial. 3, it's a trinomial. Easy enough. Or we can classify them by their height or their degree. A degree of 1 is called linear, degree 2 is quadratic, and degree 3 is cubic. Now, there are also a couple of, let's call them special cases you should know about. First is the constant polynomial. This is just a number, like 9. Its degree is actually 0, because you can think of it as 9 times x to the power of 0. Then you have the zero polynomial, which is just the number 0. And its degree is weirdly undefined. Why? Well, because is it 0 times x squared or 0 times x to the 5th? There's no way to tell what the highest power is, so we just say it's undefined. Okay, for our last section, we're going to flip the script. We've been all about construction, right? Now let's talk deconstruction. We're going to learn how to find the secret keys that can unlock a polynomial's structure and show us what it's really made of. And this incredibly powerful tool is called a zero. Now, careful, it's not just the number zero. A zero of a polynomial is any value that, when you plug it in for the variable, makes the entire polynomial equal zero. It's the magic input that makes the output completely vanish. Yeah, let's just forget the technical jargon for a second. Think of a zero as a magic number. You feed it into your polynomial machine, hit go, and poof, the whole thing just turns into zero. So why do we care? Why is this so important? Well, it's because of this amazing connection. Every single time you find a zero, you have also found one of its factors. And a factor, well, that's one of the original smaller pieces that got multiplied together to build your polynomial in the first place. So if you figure out that the number 2 is a zero, you automatically know for a fact that x minus 2 is one of its original building blocks. This isn't just a party trick, by the way. This is how we solve real-world problems. So really, it all boils down to this simple 3-step process. Step 1, you hunt for a zero. Step 2, that magic number instantly reveals one of the polynomial's factors. And finally, step 3, once you have those factors, you've successfully taken apart the original structure, deconstructing it right back down to its core components. So there you have it. We've seen that polynomials are literally the building blocks of algebra, and their zeros are the secret keys to taking them apart again. And this ability, this skill to both build and deconstruct, it's absolutely fundamental to solving problems everywhere, from science and engineering to economics, which really just leaves us with one final question to think about. Now that we have the key, what other secrets are we going to unlock with it?